Welcome to Joe's Classroom and the lecture series on frequency domain analysis. In this lecture, we are going to understand about the Bode plot of systems with transfer functions having non-zero real values as their poles or zeros. Before going into today's topic, let us have a quick review of what we learned in the previous lecture. In the previous lecture, we started to understand about the Bode plot, and we started with systems with poles and zeros at origin. If you take a system with pole at origin, then the transfer function of the system is given by g of s equal to k by s power n, where n is the multiplicity of the poles at the origin, or n is the number of poles at the origin. In that case, the magnitude plot is a straight line and it will pass through 1, 20 log k, that is 1 radians per second and 20 log k decibels, and it will have a slope of minus n times 20 decibels per decade. And if you take the phase plot, it is also a horizontal line and it passes through or passes at minus n times 90 degree. So both are straight lines. And similarly, if we take a system with zeros at the origin, then the transfer function is given by g of s is equal to k into s power n. The s term comes in the numerator, and here n is the number of zeros at the origin. In that case, the magnitude plot is very similar to that of system with poles at origin, but only difference is the slope. There the slope was minus n times 20 decibels per decade, and here it is going to be plus 20 n decibels per decade. And similarly, phase plot is also the same almost, except the sign. Here, there it was minus 90 n degrees, and here it is plus 90 n degrees. The sign becomes positive because the s terms appears in the numerator. So with this background, let us move on to understand the Bode plot of systems with transfer functions having poles and zeros as non-zero real values. So if we take this as the transfer function, g of s is equal to k by 1 plus ts the whole power n, let us examine its pole. So let us take the denominator. If I equate the denominator equal to 0, then I will have 1 plus ts equal to 0 as a characteristic equation. And of course, for n number of factors, I will get n number of these equations, and each equation will have a solution of s is equal to minus 1 by t. So the pole of the system is minus 1 by t, and the number of poles will be equal to n. Otherwise, I can say that for this system, there are n number of poles at minus 1 by t. T being a real value. We all know that we are all dealing with systems with the differential equations having constant coefficients or real constant coefficients, and therefore t is going to be a real value. Since t is a real value, minus 1 by t is also a real value. And you'll be able to notice that this is a non-zero value. T is not going to be infinite, and therefore it is going to be a finite value. And if this is going to be a finite value, this pole is going to be a non-zero. So therefore, this transfer function represents systems with non-zero real poles. Okay, the number of poles is equal to n. So this system will have n number of poles at minus 1 by t. So having known this, let us try to understand what is going to be the magnitude and phase of the system with respect to frequency. So to find out that, I should find out g of j omega. So g of j omega is obtained just by replacing s term by j omega term. So To get the magnitude and phase, I should find out the magnitude of the numerator and the denominator separately. If I take the numerator is going to be a constant k, and therefore its magnitude is going to be k. However, in the denominator, we have got a complex number. We know if I have a complex number in the form of a plus jb, then the magnitude of the complex number is root of a square plus b square. That is where a is the real part and b is the imaginary part. If I apply this, I will get the magnitude of g of j omega as k by square root of 1 plus t square omega square the whole power n, because here it is a is equal to 1 and b is equal to t omega, and therefore it is a square plus omega is 1 plus t square omega square. So to find the gain in decibels, we have to take 20 log of g of j omega, and here we have to take the magnitude. Since the magnitude has been already found, you can apply this formula. Okay, and before that, g of j omega magnitude is k by this particular term, and it is written here. So if you look at this, is of the form log a by b. Log a by b is equal to log a minus log b. Please note that here the logarithm means the logarithm to the base 10. So if I apply this formula, I can get as 20 log k minus 20 log of this square root of this term, the whole power n, I can write it as n by 2. So another logarithm formula we know is log a power m is equal to m into log a. So if I apply this formula to this, n by 2 comes here. Okay, and therefore it is going to be 20 into n by 2, that is going to be 10n. So the final formula or the final expression to calculate the magnitude of the system in decibels is going to be this. Please note, here there are two terms. One is 20 log k corresponding to the numerator of the transfer function, and the other term is 10n log of 1 plus t square omega square. So this corresponds to the denominator term in the transfer function. So this is going to be the final expression. Now it's time to get the angle of g of j omega. We got the magnitude in decibels, and now it's time to get the angle of g of j omega. So if you take this as a complex number totally, I've got a numerator and denominator, of course. So the numerator is a constant k, so I can take this constant k here, and this I can write it as 1k into 1 by this particular term. Again, this I can write it as k into 1 by 1 plus j t omega, the whole power n. There is nothing wrong in it. Okay, so we know that if I have a complex number, okay, which is multiplied n times, then the angle of the z power n is going to be n into angle of z, because when it comes to angle in a product of two complex numbers, we add the angle of the two complex number. Therefore, if z is multiplied n times, then the angle of z power n is going to be n times angle of z. So even in this case, if I want to find out the angle of this entire term, it is just sufficient to find out the angle of whatever term is inside the brackets and multiply it by n times. So therefore, if I take only this term, angle of this term, I can write it as angle of the numerator minus the angle of the denominator, because angle of z1 by z2 is equal to angle of z1 minus angle of z2. So this is what you get. If you take this is a real positive number. For any real positive number, the angle is going to be 0. And if I have a complex number of the form a plus jb, then angle of z is going to be tan inverse of b by a. So here this is b and this is a. So therefore I can write like this, and this is what I get. And again, so we saw that this is the expression for angle in the case of z power n. So I got the angle of this, and therefore to get the angle of this entire term, it is just sufficient to multiply it by capital N. So the angle of g of j omega is n times of this minus n times tan inverse of t omega. So for this transfer function, this is a system with non-zero real pole. Then the magnitude is given by this expression, and the angle of the system is given by this expression. To have a better understanding of the shape or how the Bode plot of this particular transfer function is going to look like, let us take a specific case. So I'm taking a specific case with k is equal to 1 and n is equal to 1 and t is equal to 0.1 second. Okay, t I take it as 0.1 second. So this is going to be a system with order n equal to 1 and t equal to 0.1. So for this system, obviously the pole is minus 1 by t. So that's what we saw initially. And therefore s is equal to minus 1 by 0.1, and that is equal to minus 10. Pole is at minus 10. Please note that. Also, the magnitude in decibels is given by this expression. In general, k is here 1, and therefore log 1 is going to be 0 and 20 log k is going to be 0, and this term is going to vanish. And what about this? N is equal to 1, and therefore minus 10 log of 1 plus 0.1 square omega square. That's what we get. If I plot this in a semi-log sheet as a function of omega, this is what is going to be, the shape of this magnitude plot. Okay, so I just plotted this magnitude as a function of omega for a frequency range of 0.01 to 10,000. And similarly, the angle is given by minus n times tan inverse of t omega. So again here n is equal to 1 and t is equal to 0.1. If I replace with those values, this is what is going to be the magnitude plot. And this is also a a function of omega. And if I plot it on a semi-log sheet, this is what is the graph we will get. If you look at this graph, okay, for smaller values of omega, as omega tends to 0, okay, towards 0, what is g of j omega? If I put omega equal to 0, apply the limit omega equal to 0, then this is going to be tan inverse of 0. Tan inverse of 0 is 0 degree. And as omega tends to infinity, to the higher values of omega, if I apply that limit here, it is going to be tan inverse of infinity, and tan inverse of infinity is going to be 90 degree, and therefore it is minus 90 degree. So what we understand is, as the frequency increases from 0 towards infinity, the angle changes from 0 to minus 90 degree. Okay, so that's what we see here. And also, when it comes to the magnitude plot, we understand that up to a frequency of almost 10 radians per second, the magnitude is 0 decibels, which corresponds to a magnitude of 1. For all other higher frequencies, the magnitude is negative in decibels, that means the magnitude is less than 1. So all higher frequencies the system is going to attenuate, whereas all lower frequencies it is going to allow. So that's what we understand from this. So therefore, this system I can call it as a low pass filter. It allows only the low frequencies and it attenuates all the higher frequencies. Okay, so let it be there. Anyhow, so when we compare this magnitude and phase plot with those magnitude and phase plots what we learned in the previous lecture, we can notice a major difference. The previous case, in the case of integrators and differentiators, both the magnitude and phase plots were simply straight lines. Straight lines. Okay, here also we got straight line, where we got a horizontal straight line, and here it is, we got an inclined straight line. Okay, magnitude plot was an inclined straight line. But here the major difference is it is not so. It is not a straight line here, both magnitude and phase plot. Okay. However, when Bode observed, these magnitude and phase plots, he saw some straight lines in this also. He saw, this both this magnitude and the phase plots were piecewise linear. Piecewise linear in the sense this is linear here, this is a straight line in this region, and here also this is a straight line. If we look at this phase plot, this is straight line, again a straight line, and this is straight line. So he observed this magnitude and phase plots as straight lines. Okay, he drew some straight lines, and obviously these straight lines are nothing but the asymptotes of these curves. When he replaced this, nonlinear magnitude and phase plots with piecewise a linear graph with the help of this asymptotes, this is what he got. So here a straight line with zero slope, and here is another straight line with some finite slope, and here also there is three straight lines in the phase plots, one with zero, two lines with zero slopes, and one line with some finite slope. And he called this Bode plot as the asymptotic Bode plot. Also, when he drew this asymptotic Bode plot, he observed, certain interesting things. The first interesting thing that he observed was this Bode magnitude plot, otherwise asymptotic Bode plot, changed its slope at some frequency. Okay, at some frequency. So this frequency he called as the corner frequency. You look at here. Here the slope is 0 decibels per second. Sorry. Here the slope is 0 decibels per decade. And here the slope is, minus 20 decibels per decade. You will be able to observe. So the slope changes from 0 decibels per decade to minus 20 decibels per decade at a frequency of omega is equal to 10. What is interesting about that? He found that this frequency is nothing but 1 by t. That is nothing but the pole. We got the pole as minus 10, and here, the corner frequency is the same pole 10. Only thing is it is only the magnitude. The frequency cannot be, negative. So here it is going to be only the magnitude. So this frequency he called as the corner frequency. And therefore, in general, I can define the corner frequency as the frequency at which the asymptotic magnitude plot changes its slope. And the corner frequency is going to be equal to 1 by t. Very, very, very important. The corner frequency is always equal to 1 by t. So you know, to find out the corner frequency of any transfer function, first of all, this transfer function should be in a time constant form. Then only you can get the t value easily. So it has to be in the form 1 plus ts or 1 plus st. And now the question is there any relation between this corner frequency and the change in slope of the asymptotic phase plots? Yes, there is some relationship. So when it comes to the asymptotic phase plot, the slope changes at 2 points. At one point before the corner frequency and at another point after the corner frequency. Before the corner frequency, you will be able to observe that this slope change occurs at 0.1 times of the corner frequency. For example, in our case, the corner frequency is 10 radians per second. 0.1 into 10 is going to be 1 radians per second. And in the same way, the other change on the other side of the corner frequency, the change is going to occur at 10 times the corner frequency, or in this case, it is 100 radians per second. So 10 times 10 is going to be 100. So now we understood that when it comes to the Bode plot of transfer functions with non-zero poles, there is a exact Bode plot and there is an asymptotic Bode plot. Of course, the asymptotic Bode plot is a bit approximate at certain region. Particularly in this region, it is not exactly coinciding with the exact Bode plot. So we call this asymptotic Bode plot as an approximate Bode plot also. But usually it is called asymptotic Bode plot. So this is what is the exact Bode plot and this is the asymptotic Bode plot. Here also this is the exact, the red line represents the exact phase plot and the green line represents the asymptotic phase plot. Now if I zoom this part, there is some mismatch between the exact and asymptotic Bode plot. If I zoom it like this, you will be able to find out that this difference, the difference between the exact Bode plot and the asymptotic Bode plot is this. The difference or the error is going to be maximum at the corner frequency. And both analytically and graphically, we can prove that this maximum error between the asymptotic Bode plot and the exact Bode plot is going to be 3 decibels. So the maximum error between the asymptotic and the exact Bode plot is 3 decibels. Okay, that's interesting. And therefore, it gives me an idea to sketch the exact Bode plot without finding the magnitude for all the frequencies. That is what is the point you should take away from this part of the lecture. See, what I understood was there is a slope change happening at the corner frequency and the corner frequency is given by 1 by t. So if I give a transfer function like this, you will be able to identify the value of t immediately from the transfer function if you write it in a time constant form, and immediately you can find out the corner frequency. And once you locate this corner frequency, you understand that up to this corner frequency, there will be a straight line with 0 decibels per decade slope. And beyond this corner frequency, there will be another straight line with some finite slope. So this is what. So I can easily draw these lines if I know the slope of this line. Anyhow, we will see how to find out the slope of this line later. There is no doubt about this line, the slope of this line. This line is always going to be, the 0 decibels per decade line, and this will have a finite value, and we will see what is going to be the finite value of this slope. And at the same time, though this slope is known, we may not know, where this line has to lie. For example, it can be here, or it can be here, or it can be above, or it can be 0 decibels. Why not? Anyhow, we will see that. We will see that in the coming slides. So once you draw the asymptotic Bode plot, at the corner frequency, I said that, the maximum difference is going to be 3 decibels. So you mark the 3 decimals down, okay, and now you can approximately sketch this. So even without, knowing the each and every value for the each and every value of this magnitude for different values of frequencies, I could I could easily get this Bode exact plot from Bode asymptotic plot. So in control theory, Bode asymptotic plot plays a major role in the analysis of systems. So in the entire lecture and in the entire course of this frequency domain analysis, from this point onwards, we will be mostly focusing on this asymptotic Bode plot. So now it is necessary that we should know the slope of this line and the magnitude of this line. If I know the magnitude of this line and if I know the slope of this line, no problem. I for any given transfer function, I can draw the asymptotic Bode magnitude plot. So let us find that. Let us take the generalized case. G of s is equal to k by 1 plus ts the whole power n, and we know this is the expression to calculate the magnitude. Let us take a case of frequency lesser than 1 by t. So when I say 1 by t, it means that it is a corner frequency. We already understood. And I'm just going to consider all the frequencies lesser than this corner frequency. Okay. In that case, you can see that t square omega square is going to be far, far lesser than 1. I have illustrated with some examples. From these examples, you can very well see that t square omega square is always lesser than 1. I have taken two cases with t is equal to 0.1 as well as t is equal to 20. So whatever value you take for frequencies lesser than 1 by t, this value, the product of t omega squared, is far, far lesser than 1. The cases show here. In that case, if I take these two terms, this one is going to dominate in this. So therefore, this t square omega square I can neglect. If I neglect, the entire term is almost equal to 1. In that case, if I replace this entire term with 1, this is going to be log 1 and this term is going to vanish. And therefore, for frequencies lower than the corner frequency, the magnitude plot is going to be a straight line at 20 log k. So we got the magnitude of this line. This magnitude of this line has to be at 20 log k. Here the value of k is 1 and therefore we got it as 0 decibels. So this magnitude or the magnitude of this line, the horizontal line before this corner frequency, is decided by the value of k, and it is equal to 20 log k. Okay, and this is a 20 log straight line with a slope 0 decibels per decade. And if it means we understand that for frequencies lower than the corner frequency, the contribution by this, the denominator term is very, very negligible to the gain. The gain is contributed only by this K, open loop K. Okay, that is an important point to note. Please note this will be a very important point when you when you start to plot or sketch Bode plot for systems with more number of poles and zeros. Okay, so this will be a very useful point. So there is no contribution by this denominator term for frequencies lesser than the corner frequencies, and the contribution is only by this gain K. And if you take frequencies greater than 1 by T, what's the condition? T square omega square is going to dominate, and that is going to be very, very larger when compared to 1. See, again, I have given some examples. You can just look at it. I'm not going to explain. Okay, in that case, this 1 could be neglected, and this is going to be T square omega square. T square omega square. This 1 could be neglected. Okay, in that case, this expression becomes like this one. And now this 2, I can bring it here, and there it becomes 20 yen. So now, this line, the equation of the line, beyond this corner frequency is going to be this 20 log k minus 20 n log of t omega. So this is the equation of the line, beyond this frequency. This equation is represented by this expression. Okay, now my objective is I should know the slope of the line rather than the equation of the line. Okay, rather than the equation of the line, what I need is the slope of the line. So then it is going to be easy for me to sketch the asymptotic Bode plot. So let me find out the slope of this line. So you can very well say this is going to be of the form mx plus c. This can be taken as m, and this log t omega can be taken as x, and this is going to be the constant c. So if I compare like this, the slope is going to be minus 20n, but still there will be a small confusion because of this t term in this. So to clear that confusion, I'm going to take two frequencies 1 decade apart. I'm going to take one frequency at omega is equal to 1 by t, and another frequency 1 decade apart, that is 10 times 1 by t. Let me substitute omega is equal to 1 by t and omega is equal to 10 into 1 by t. See, this is what happens. At this frequency, obviously t omega is equal to 1, and if I substitute this, this term will vanish and the term will reduce to 20 log k. Okay, and at 10 times 1 by t, that is at frequency 1 decade apart from omega is equal to 1 by t, if I substitute, this is what I will get. So you can try doing the substitution. So if you clearly observe these two equations, since the magnitude reduces by minus 20n, the slope is minus 20n decibels per decade. And therefore, if I go back, line is going to have a magnitude of 20 log k, and this line is going to have a slope of minus 20n. So therefore, if I know these two parameters and this corner frequency, immediately I can draw the Bode asymptotic plot. Okay, yeah, we'll move on. So yeah, this is what I explained. Again, it's illustrated, and this is a 0 decibels per decade line, and since k is equal to 1 here, it is 20 log k is equal to 0 decibels, and here after that corner frequency, it is going to be a straight line with minus 20 dB per decade, because n here is 1, and therefore minus 20 n is equal to minus 20. So very immediately I can sketch this asymptotic Bode plot. So let us try to remember some important points for this transfer function with pole at some non-zero values. Then the corresponding asymptotic plot will have only the straight lines, and the slope of the asymptotic plot changes at the corner frequency. Omega is equal to 1 by t, and please remember this 1 by t is nothing but the magnitude of the pole also. And for omega lesser than 1 by t, lesser than the corner frequency, it is going to be a straight line, horizontal straight line with a magnitude of 20 log k and slope 0 decibels per decade. And for frequencies greater than the corner frequency, the slope of the line is going to be minus 20 n decibels per decade, and this line again passes through the corner frequency and 20 log k. Okay, and the phase plot changes its slope at 0.1 times the corner frequency, and sorry, this is 10 times, not 100 times, and 0.1 times the corner frequency and 10 times the corner frequency. Now let us take another example. So here the transfer function chosen is g of s equal to square root of 10 divided by 1 plus 0.5 s the whole square. And here obviously k is equal to square root of 10 and n is equal to 2 and t is equal to 0.5. So therefore the corner frequency I can find as 1 by 0.5. It is nothing but 2 radians per second. So this is 10 power 0, this is equal to 1, and this is 2. So I located the corner frequency. Once I locate the corner frequency, what I need to find out is what is going to be the value of 20 log k and what is going to be the slope of this line beyond the corner frequency. So the 20 for frequencies lesser than the corner frequency, the magnitude of the line is going to be at 20 log square root of 10, because k is equal to square root of 10, and that you can calculate as 10 decibels. So you draw a line at 10 decibels with zero slope. And for frequencies greater than the corner frequency, that is 2 radians per second, the slope is going to be minus 20 n, that is n is 2 here, and this is going to be minus 40 decibels per decade, and I have to move by 1 decade and I have to reduce the magnitude by 40 decibels. So I will get a slope of minus 40 decibels per decade, and I can draw the asymptotic line. Okay, so 1 decade I'm taking from 2 to 20. Fine. So this is how you can sketch the asymptotic Bode plot for any transfer function with poles at some non-zero values. So having understood this, let us now move on to understand about systems with zeros as non-zero values, not at the origin, non-origin zeros. Okay, so this is what is the expression we have already seen. This is for the poles, and if I compare the systems with poles and zeros, okay, we clearly understood the difference is going to be in the signs. Obviously, this negative sign is going to become as positive sign here, and this negative sign is also going to be a positive sign here. This you can analytically also verify as we did for poles. You can do it for zeros also. I just leave it to you. Anyhow, this is going to be the final expression. Also, if I take the case of systems with poles and zeros, what is going to be the the line for frequencies lesser than the corner frequency and frequencies greater than the corner frequencies. So for frequencies lesser than the corner frequencies, in the case of poles, if the transfer function looks like this with this term in the denominator, okay, then the magnitude of the line for frequencies lesser than this corner frequency is this 20 log k. That is not going to change here in the case of zeros also. When it comes to zeros, the transfer function is going to look like this 1 plus t is the whole power n term is going to come in the numerator. Okay, and the line magnitude for frequencies lesser than the corner frequency is 20 log k, as in the case of poles. Whereas for frequencies greater than the corner frequency, the slope of the line is going to be positive here in the case of zeros when the 1 plus ts term comes in the numerator. Please note that that is the only change. Okay, and we will try plotting the asymptotic Bode plot for an example with zeros. So let this be the transfer function. G of s is equal to 1 plus 2s. Clearly k is equal to 1 and the order is also 1 and t is equal to 2. What's the corner frequency? It is 1 by 2. 1 by 2 is equal to 0.5 radians per second. Immediately identify the 0.5. This is 0.1 and this is 2, 3, 4 and 5. So this is 0.5 radians per second and that is going to be the corner frequency. And 20 log k, k is equal to 1 here. 20 log k is going to be 0 decibels. So up to this corner frequency, it is going to be a horizontal straight line at 0 decibels. For frequencies greater than 0.5 radians per second, that is a corner frequency, it is going to be plus 20n because it's a 0 and this term is appearing in the numerator, and therefore it is 20 into 1 is equal to 20 decibels per decade. So move by 1 decade the frequency axis and increase by 20 decibels. You get an increasing straight line with a 20 decibels per decade. So that's how you get the magnitude plot. Fine. And if I want to get the exact plot again, just take 3 decibels above this value at the corner frequency. Okay, here it is going to be positive. The error is going to be positive, and you have to take plus 3 dB above it, and you can sketch the exact Bode plot if you want. And let us have a look at the phase plot also. For this, what we will write the phase as angle of g of j omega is equal to tan inverse of 2 omega, tan inverse of 2 omega, tan inverse of t omega. Here it is going to be plus n because it's a 0. N is equal to 1 and therefore we got 1 into tan inverse of 2 omega. It's nothing but tan inverse of 2 omega. If I plot, this is what you will get. And how usually actually we plot is we take different values. For example, you may start from 0.01, 0.03 and 0.07 or something, again 0.1. Take all possible values of omega at equal intervals, so that you get a smoother plot, and find out the value of this angle substituting in this expression, and you take the values as if you plot for any function, any given function. How you plot the graph, that is how you have to do it. Okay, and one important thing to note here is when the omega value tends to 0, it is going to be 0 and tan inverse of 0 is 0. So for smaller values of frequency, it is 0 almost, and it starts from 0 And as omega tends to infinity, this is going to be infinity, and tan inverse of infinity is going to be 90 degrees. So it starts from 0 degree and reaches the 90 degree as frequency tends to infinity. Now here is another second example. K value is 0.00316 and n is equal to 3 and t is equal to 0.04. Corner frequency is 25 radians per second. 25 radians per second is located here. See, one important thing to note here is this is 2, therefore this is 10, this is 20, and 5 should be, don't take exactly at 50%. So this is a logarithmic scale. You should be able to notice that here, if this is 1, 2, 3, 4, 5, 5 comes somewhere beyond the midway. So when you take 5, 25, you should take a little farther than the midpoint of this. So that is why I've taken it as taken this 25 radians per second here. So the corner frequency is identified, and for frequencies lesser than the corner frequency 25 radians per second, it is going to be 20 log k. You got the value, it is minus 50 decibels, and the slope is 0 decibels. It's a horizontal line. Draw a straight line up to this corner frequency, and n is equal to 3, and the slope is going to be 60 decibels per decade. Identify the point here at 60 decibels per decade positive. Okay, draw the line. So you get the asymptotic Bode plot, and if you want to get the exact Bode plot, do a change here, you can get it. And the and the phase plot is shown here as the expression is angle of g of j omega is 3 into tan inverse of 0.04 omega, because n is equal to 3 and t is equal to 0.4. As I said, you have to find out the angle for different values of this frequency and plot it. Important thing to notice, as 0 omega tends to 0, this is going to be 0, and this entire thing is going to be 0, and it is going to start from 0. And but as omega tends to infinity, this is going to be tan inverse of infinity, that is 90. 3 times 90 is 270, so it reaches 270 as omega tends to infinity. So the starting point and the ending points might be important, because maybe when we study about these polar plots and all, that will be useful. So the point to remember here is the transfer function, if it is in the form of k into 1 plus ts the whole power n, it is represents a 0, non-zero at some non-origin value, and therefore the asymptotic Bode plot, both magnitude and phase plot, are straight lines before corner frequency and after the corner frequency. What are the values? 20 log k, and a line with plus 20 n decibels per decade. Again, here there's a mistake, so it's a 0.1 time 1 point t and 10 times 1 point t. The Bode phase plot will change the slope at these values. So with this, here I have given more examples in this table. So this gives a clear picture of how you should get all these values. See, if this term, the 1 plus ts terms, appears in the denominator, it is going to be pole. And if it appears in the numerator, it is going to be 0. And the order is given by this power. Okay, here it is 1, 2, 5, 1, 3, 4. Okay, this is what is order, and this is going to be the value of n. And the corner frequency is given by t, 1 by t. Yeah, you get all the corner frequencies. And for frequencies lesser than this corner frequency, the magnitude can be found by 20 log k. This is what, so this is what we find. Okay, and for frequencies greater than the corner frequency, slope of the magnitude you can plot, you can find from the value of n. It is going to be minus 20 n decibels per decade in the case of pole, and plus 20 n decibels per decade in the case of, the zeros. Okay, so you got this, and this is going to be minus n times tan inverse of t omega in the case of pole, and plus n times tan inverse of t omega. So if you know this, immediately you can sketch the asymptotic Bode plot. But important point to note here is the corner frequency is something associated to the t value 1 by t, and the magnitude of the horizontal line for frequencies lesser than 1 by t, the corner frequency corresponds to 20 log k. It corresponds to k, and the slope of the magnitude plot beyond the corner frequency gives you an idea about the order of the pole. Okay, order, number of poles, n value you get. So if you know these three values, immediately you can get the transfer function also. That's the point. So once you are given the transfer function, you should be able to get the asymptotic Bode plot. And if the asymptotic Bode plot is given, you should be able to get the transfer function also. So how do you get? If you want to know the transfer function, you should know the value of t, you should know the value of k, and you should know the value of n. If you know these three values, you're done with. So how do you find out the t? From this corner frequency. How do you find out the value of k? From 20 log k, that is the magnitude of the horizontal line before for frequencies lesser than the corner frequency. And what is the slope of the line beyond the corner frequency? That gives you an idea about n. So you can get it. So to illustrate this, I'm just taking an example, and with this example, we'll be winding up this lecture. So this is the Bode plot given. Please note, this is not necessary. The phase plot is not necessary to find out the transfer function, but you can very well use this phase plot to verify whether your result is correct. So let us try to find out the transfer function for this. So what you should do? First thing is to identify the corner frequency. We find the corner frequency as 4 radians per second. Therefore, t is equal to 1 by omega. Corner frequency is equal to 1 by t, and therefore t is equal to 1 by corner frequency. So therefore, we got the value of t. Now you need to get k and n. How do you get the value of k? Find this value. Okay, so I understand that it is 28 dB. Okay, so this is 20, the midway is 30. Okay, so something lesser than that is 28 dB. So 20 log k is equal to 28. So from this you can get the value of k as explained here. And now the remaining parameter to be found is only the value of n. How do you find n? From the slope of this line. Yeah, from this move by 1 decade. Okay, so 4 to 40. See what is the change in the magnitude. It is plus 8 decibels per decade. So n is going to be 4. Okay, n is going to be 4, and because it is a positive slope, it is going to be a 0. So this term is going to appear in the numerator. So the format is k into 1 plus st the whole power n, and we got all the values. K we got it as 25.119, and t we got, and n we got. That's it. So for the given transfer function with poles or zeros at values other than the origin, okay, then you should be able to get the Bode plot, asymptotic Bode plot, and the phase plot. Or if the asymptotic magnitude plot is given to you, you should be able to find out the transfer function of the system also. That is what is explained in this lecture. Hope you understood, and if you have any doubts, you can post it in the comments. Thanks for watching.